Welcome to our discussion on temperature in large language models. Today, we'll explore what temperature really controls in these models, a topic often misunderstood. Essentially, temperature dictates randomness in generated responses. A higher temperature increases variability, leading to more creative outputs, while a lower temperature yields more focused, predictable results. Understanding this balance is crucial, especially when explaining it under the pressure of a technical interview. Let's dive in and clarify this key concept. Let's explore the common understanding of temperature in AI models. Generally, higher temperature means more randomness and creativity, while lower temperature leads to deterministic outputs. However, we should question three key claims: that temperature adds randomness, that higher temperatures make models creative, and that a temperature of 0 always results in identical outputs. Each of these points has nuances that challenge their straightforward acceptance. Let's explore how a model generates one token. The process begins with sampling, where we calculate Logits for possible tokens. Before applying the Softmax function, temperature is introduced, adjusting the model's confidence in token selection. This influences the diversity of outcomes. Finally, randomness is inherent in the sampling step, ensuring variation in the generated tokens, irrespective of the temperature setting. Together, these steps define how a model predicts its next token. Let's dive into Logits. In a model's final layer, it outputs a vector with one number for each vocabulary token. So if our vocabulary has 100,000 tokens, we get 100,000 numbers, known as Logits. These Logits can be any real number, not probabilities yet. That's where Softmax comes in. It transforms Logits into a probability distribution, where each value is between 0 and 1, summing to 1, ready for sampling. Let's explore the role of temperature in model predictions. Initially, the model outputs raw scores called Logits, such as 5, 3, and 1. Each of these Logits is divided by a temperature value, 2, before applying the Softmax function. This step converts the scaled Logits into a probability distribution. During sampling, a token is drawn from this distribution. Remember, temperature doesn't add randomness, but reshapes the distribution from which we sample. Let's explore how temperature affects Logits and their probability distribution. With a temperature of 1.0, the Logits 5, 3, 1 lead to a dominant first token at 84%. Raising the temperature to 2.0 gives us a more balanced distribution with 57%, 30%, and 13%. Conversely, lowering the temperature to 0.5 sharpens the distribution, making the first token overwhelmingly likely at about 98%. This demonstrates how temperature can control distribution sharpness in Softmax. Let's dive into the concept of temperature in probability distributions. High temperature compresses differences between Logits, resulting in a flatter distribution. This means lower-ranked tokens have a real chance of being selected. On the other hand, low temperature amplifies differences, creating a sharper distribution where the top token dominates. The key takeaway is that temperature doesn't determine randomness. Instead, it controls how concentrated the distribution is, influencing how broadly we sample. Let's talk about why labeling AI as creative can be misleading. The model itself doesn't possess creativity. Instead, it operates on probability. At higher temperatures, it picks less probable tokens, leading to unexpected outcomes. While this seems creative to us, it's actually just a willingness to explore less likely options. The model isn't smarter or more inspired. It's simply sampling from a wider range of possibilities. Let's explore what happens when temperature, T, approaches 0 in greedy decoding. Dividing Logits by a near-zero value forces them toward infinity, making the highest Logit almost certain. At this point, sampling disappears, and the model selects the argmax. However, setting t to 0 might still yield different results due to floating point precision errors at the GPU level. Mentioning this nuance in interviews shows practical experience beyond just reading the documentation. Welcome to Chapter 2, where we delve into the intricacies of token selection. We'll explore temperature, top K, and top P, three critical factors that shape how tokens are chosen. Each of these parameters influences the process in unique ways and at different stages. By grasping the nuances of these techniques, you'll move beyond surface-level answers to generate more nuanced and robust responses. Let's dive in and understand how each of these elements plays its part. On this slide, we explore three mechanisms for controlling model outputs. First, temperature acts before the Softmax function, dividing Logits to adjust the distribution's sharpness or flatness. Next, top K sampling occurs post-Softmax, retaining only the top K tokens and setting others to 0, effectively limiting the selection pool. Lastly, top dash or nucleus sampling dynamically accumulates tokens until their combined probability exceeds a given threshold, offering flexible pool sizes. In this slide, we're comparing top K and top P sampling methods. Top K uses a fixed number of tokens, say 40, no matter how the data is spread out. On the other hand, top P adapts to the distribution's shape, keeping as few as 3 or as many as 300 tokens, depending on the model's confidence. This adaptability makes top P more robust when dealing with different types of data distributions. Let's explore the execution order in generating text. We start with temperature scaling, which adjusts how confidently the model selects words. Next, softmax probabilities convert raw scores into a probability distribution. Finally, top K and top P sampling choose the most likely word candidates. Each stage focuses on a specific part of the process, working together without redundancy, ensuring an efficient and coherent text generation. Let's discuss a common technique that optimizes language model outputs, using a temperature of 0.7 and a top P of 0.9. Temperature slightly narrows the distribution, while top P trims the low probability tail, providing a balanced output that reduces nonsense without sacrificing diversity. This works because temperature shapes the overall distribution, while top P handles the tail noise. Avoid setting both temperature and top P too low, as this can result in overly conservative outputs. Welcome to Chapter 3, where we'll delve into the practical application guide. In this section, we'll explore how to take the concepts we've learned so far and apply them in real-world scenarios. Get ready to gain hands-on experience and insights that will enhance your understanding and skills. Whether you're a beginner or looking to deepen your expertise, this chapter is designed to provide you with the tools you need for practical success. When choosing a temperature setting for your tasks, consider the following. Low temperatures, ranging from 0.0 to 0.4, are ideal for tasks requiring precision and factual consistency, like code generation and data extraction. Medium temperatures, between 0.5 and 0.8, are great for balanced interactions, providing coherent yet varied responses. For creative endeavors, go high at 0.9 or above, embracing diversity and innovative ideas, even if it means occasional, unconventional outputs. When working with models, don't just rely on default settings. Defaults cater to general use cases, but your task has unique needs. Run experiments tailored to your specific tasks and datasets. For instance, set parameters like temperature, Based on your task's requirements, determinism might be crucial for structured tasks. Test different values in pair settings like top PEA or top K intentionally. Always document your choices clearly. You'll need to explain them during evaluations. Let's delve into the interview answer framework. It starts with understanding where temperature acts, which is just before softmax, scaling the probability distribution. It controls the concentration, not the randomness, sharpening or flattening it. Randomness itself always occurs during sampling. At zero temperature, we encounter greedy decoding with a nod to floating point nuances. Finally, temperature, top K, and top P interact at sampling, shaping, and truncating the distribution. Let's explore what makes this answer exceptional. First, there's mechanistic precision. You accurately describe dividing Logits before applying softmax, avoiding vague terms like controlling randomness. Then, you correctly attribute randomness to the sampling process, not the temperature, a common error among candidates. Your production awareness shines when you address the floating point edge case, reflecting real-world expertise. Finally, your system's thinking is evident as you explain how temperature, top K, and top P works together as a cohesive pipeline, rather than isolated settings. Let's dive into the key takeaways about temperature and model sampling. Temperature reshapes, not randomizes, by adjusting Logits before softmax to control the probability distribution sharpness. At zero, it leads to greedy decoding, selecting the highest probability without randomness, but floating point quirks can still affect outcomes. Temperature, top K, and top P each have unique roles, working together for precise output control. Always align your temperature choices with your task needs and justify them through experimentation.